We're continuing with section 14.6 and looking at evaluating iterated integrals. These are triple integrals. Now you will see in this section this notation of three integrals with a Q underneath. That Q is going to represent a solid region in space of some function of x, y, and z with a differential volume dv. And that dv, we've looked at the arrangements of dz, dy, dx, and the bounds for the definite integrals determine the bounds of the region. Here's an example. Suppose this blue shaded region is a solid region. Well, if we slice it parallel to the xy, xz, and yz planes, we end up with these little boxes here, and we can approximate the volume of that solid region by adding up the volumes of all those little boxes. And we're going to represent those little boxes as a differential volume. So the sum of all those differential volumes will be equal to the volume of the solid. So if you make those boxes smaller and smaller and smaller, that's going to approximate the volume of the solid region. And we can then write this as a triple integral to give us the exact volume. So again, we're looking at this notation here. When you see that triple integral Q, that region in space is going to determine the bounds of integration. And then you have some function of x, y, and z. dv is your differential volume. Now the volume, if there's nothing in front of the dv itself, this triple integral will give you the volume. So this triple integral Q is that solid region. The bounds of the iterated integral are going to be determined by the region in space. Now your dv can be either dz, dy, dx, or any arrangements, and you'll actually see that there's 6 different ways that you can arrange the differentials dz, dy, and dx. And with each arrangement, your bounds are going to be adjusted by the order of the differentials. And remember that the outside bounds must be constant with respect to the inside, and so on. To find the limits for the particular order of integration, you want to determine the innermost limits, which may be functions of the outer 2 variables. So you can have the inside bounds, in this case, can have y's and x's in it, because the order of the differentials is dz, dy, dx. Once you get those innermost limits, then you project that solid onto the coordinate plane of the outer 2 variables and determine their limits. For example, if you want to evaluate this triple iterated integral of the region Q, that solid region Q, if the order is dz, dy, dx, you want to determine the innermost bounds of z in terms of a bottom z equals to a top z equals, and those z's could be functions of x and y. And then once you get that, you're going to project that onto the xy plane, because the dy, dx are the outside differentials. So in this case, we have the region, the inside differential was dz, so you're looking at a bottom z to a top z, and then whatever that region, solid region is, you project that onto the xy plane. And where this projection falls, that's going to be your base region. And you can determine the order of the differentials and the bounds for dy and dx. Here's an example where we want to set up and evaluate a triple integral to find the volume of the solid bounded by z equals 9 minus x squared, z equals 0, y equals 0, x equals 0, and y equals 2x. You can try this one on your own, pause the video, and come back and check your work. Let's begin by sketching a graph of the solid region. The graph of z equals 9 minus x squared, that is a cylindrical surface. And if we look at the xz trace, the xz axis, 9 minus x squared is a parabola that opens down. that connects right here, or intersects the x-axis at +3 and -3, and the z-axis at +9. There is no y in this equation, so the y could be anything. So in terms of a 3D graph, you have this parabola that opens down, where it intersects the z-axis at 9 and the x-axis at +3 and -3. Since there is no y, the y could be anything, so we can extend the graph to the left and to the right and look at the graph that looks like this, kind of like a tunnel. So the solid is bounded by z equals 9 minus x squared and z equals 0. Well, z equals 0 is the xy plane. Z equals 0, and that's the xy plane. So the top of the surface is this tunnel, z equals 9 minus x squared, and the bottom of the surface is the xy plane when z is equal to 0. It is also bounded by y equals 0. The y equals 0 is the xz plane. So that would be in this direction. So we're only looking at the right half of this solid region. X equals 0. That is the yz plane. And the y equals 2x. Now y equals 2x, if you sketch that trace in the xy plane, it's a line with a slope of 2. So we can sketch that on here. Y is equal to 2x is this line. Notice there's no z here, so z can be anything. So imagine the plane that goes straight up through that. So the solid region that's bounded by those, that plane is going to intersect that tunnel at, say, something like this. It's going to intersect the tunnel. We've got this would be the solid region. And then the base of that solid region would be this part right here. So where it intersects here at +3, in fact I want to enlarge that base region. The tunnel intersects there at +3 on the x-axis, so you've got this vertical line through 3, and you have the line y equals 2x here, and then if you plug in 3 for x, you get y is equal to 6. So the region that's shaded in yellow on the 3D graph is represented by this 2D graph. This is we call this our base region. All right, so let's begin by setting up the triple integral for volume, and we can write this using the triple integral with a q underneath dv. Now since we can look at the order of the dv being dz, starting with the z's, we need our bounds for z. The bounds for z would be a bottom z, that bottom of that solid region here. Again, we're looking at all this solid region here. The bottom of that region would be z equals 0. The top of that region would be z equals whatever the surface is, which is the tunnel. So the top of that would be z equals 9 minus x squared. And then when we look at the bounds for our x's and y's, we look at the 2D region, and you can draw a vertical rectangle here. So that would be your dy dx. And then your bounds for y would be the bottom y would equal the bottom of that rectangle 0. To the top of that rectangle, y would equal that 2x. And then you need your bounds for x. If you slide that rectangle to the left here, that's x equals 0, and slide it all the way to the right here, that is x equals 3. Alright, so we can now begin writing out the triple integral, and the dv, beginning with dz here. dz would be your bottom z to the top z, from 0 to 9 minus x squared. That's the bottom. Think of this as like a little, the bottom of that slice there is z equals 0 to the top of that slice there is z equals 9 minus x squared, that part of the tunnel. And then we have our dy and dx, and we can find our dy and dx bounds by looking at that base region when we project that solid onto the xy plane. So our bounds for y would go from 0 to 2x, and our bounds for x would go from 0 to 3. Now we have a triple iterated integral that would give you the volume of that region. Begin with the inside integral. The differential is dz, so you integrate with respect to z. So it's going to be the integral from 0 to 3 of the integral from 0 to 2x. The antiderivative of dz is z, where z goes from 0 to 9 minus x squared, dy dx. When you plug in the upper bound in for z, it's the 9 minus x squared. And when you plug in 0, you get 0. So now we have this iterated integral. And the inside of this iterated integral has a differential dy, so we're going to integrate with respect to y. So it would be an integral from 0 to 3. When you take the antiderivative of this with respect to y, you're going to treat the y as a variable and everything else as a constant. So in this case, the antiderivative of these constants would be that constant times y. So we would get 9y minus x squared y. And then our bounds for y would be y equals 0 to y equals 2x, and then dx. But simplify. When we evaluate y equals 2x, that's going to give us 18y. And replace the y here with 2x, it's going to give you minus 2x to the third. When you plug in 0 for y, you get 0. So you get 18, I'm sorry, that should have been 18x, not 18y, minus 2x cubed, all of that dx. Now here we have a single definite integral. You can evaluate this and get the volume of that solid region bounded by those equations is 40.5.